Hi. In the last lab, we learned about equilibrium, predominant acids, and bases. And in this video, we'll look at a very special case where the predominant acid and base are conjugates of each other. We'll look at the case where the predominant acid is acetic acid, and we'll have 0.5 molar of the predominant acid. The predominant base is its conjugate, CH3CO2 minus, and we're going to have 0.5 molar of that as well. And the pKa of CH3CO2H is 4.74. So since these are the predominant acid and predominant base, they are the strongest acid and base present. They are the acids and bases that are going to react first. And so if we look at the reaction of the strongest acid and base, we see something very interesting happens. When we set up this reaction, the conjugate of the acid, where we remove the proton, is CH3CO2 minus, the conjugate base. And the conjugate acid, where we add the H plus to the base, is CH3CO2H. And we see that the reaction of the strongest acid and base is not actually a reaction at all, because we start off with the same, the reactants and the products are the same compounds. And this has as a consequence, since these are the strongest acids and bases present, that the initial given CH3CO2H concentration of 0.5 molar and the given initial CH3CO2 minus concentration of 0.5 molar are in fact the equilibrium amounts, because they are not going to be changed by the reaction of the predominant acid and base. So we can go straight to figuring out the pH of the solution using the initial numbers. So I'll do that here. The Ka is 10 to the minus 4.74, since that's the pKa, and that's going to be equal to the concentration of H3O plus times the concentration of CH3CO2 minus divided by the concentration of the acid itself. And we're going to now take the log of both sides, minus the log of both sides. So minus the log base 10 on the left side is 4.74. Minus log base 10 of and we can pull out that the log base 10 of H3O plus, which is in fact the pH. So we're going to end up with 4.74 equals the pH. Let me get that down a little bit. Minus the log base 10. What's remaining now is just the CH3CO2 minus concentration times the CH3CO divided by CH3CO2H concentration. And what we're going to do is we're going to bring this term over to the left, and then we'll get that. If we bring that over, we'll have 4.74 plus log base 10, and we have the concentrations of these log base 10 of CH3CO2 minus divided by log by CH3CO2H. This is equal to the pH. and we can plug in the initial numbers, the initial concentrations of the two, which were unchanged because the predominant acid and base, when they reacted, didn't change at all their concentrations. So these numbers are fixed from the initial values, and we can just plug it in, and we're going to get 4.74 plus log base 10 0.5 divided by 0.5, and they cancel, so we just have a 1 left over, and the log of 1 is 0, so 4.74 is in fact the pH. So this is a very useful log procedure, so we make it into an equation, and the equation is, if we look at this thing here, the equation is 4.74 was the pKa. So that's the pKa of the solution, plus log base 10, the initial, which is also the final A minus concentration. The A minus is the CH3CO2 minus, and divided by the initial acid concentration is the pH. And this is known as the Henderson-Hasselbalch equation. An equation that's used when the predominant acid and base are conjugates of each other. And we'll consider more the situation in the lab.